Hello and welcome back. Now, thus far, we've gotten our character to be able to run around, and that includes strafing and running forward and backward, and we have start and stop animations, and everything's looking great. But there are a few things missing from our movement. One of them is you'll notice when we turn while we're standing still, her feet just slide, and that's not okay. We want to learn how to turn in place. And another thing is when we look down or up, her gun should be following our direction of our gaze. But really, she just stares forward and the gun just stays there. And so the gun never actually points in the right direction unless we shoot straight forward ahead. So we're going to learn about turn in place animations. Now, as far as the behavior that we would like, take a look at this particular screen here. Now, here I have our character, and I'm going to turn using my mouse, and you'll notice that her feet stay still, but the top half of her body is aiming along with my gaze. And as I look up, she'll point the gun upward, and if I look down, she'll look down and point the gun down. So she's actually aiming the gun in the direction that I'm aiming, and her feet are staying relatively still. Now, there's a maximum look angle past which she will turn. So if I go past, it's 90 degrees. If I go past 90 degrees, then she'll turn using a turn in place foot animation. So she keeps her feet planted solid until I look past 90 degrees, at which point she'll turn. And so it doesn't matter how fast I turn, she'll adjust, and she'll always be turning her feet as soon as I turn too far. This is a pretty common technique used in lots of shooter games. And so this is the behavior that we ultimately want to get to. This is what we want to implement, this turn in place method. So we're going to go ahead and get started with that in this video. So let's get started. Now here I have the Bellica skeleton open. And here in the skeleton tree, I have the root bone selected. And you'll see that the root bone is this bone right here between her feet at the floor. It's not really attached to any part of her mesh at all. We can select the pelvis and see that the pelvis is connected to the root bone, but the root itself is down here at her root. And the root is basically the parent of all the bones in her skeleton. If the root moves, everything else moves with. You see, I have rotation mode selected with the root selected, and if I rotate the root, her entire body moves with her. That's how the root works. The root is the parent of the skeleton hierarchy. So if we rotate the root, the body will follow. This is key to getting her to turn in place. So the core concept with the turn in place mechanic is to understand the root bone, and if the root bone moves, the whole skeleton moves along with it. Now, in order to keep her standing still while we're rotating her upper body, we're going to be rotating the character along with the controller. In other words, when we move the mouse, the controller follows and the top half of her body will be rotating along with it. So the yaw of the character, say if we used get actor rotation and got the yaw from that, then that will be changing along with our rotation of the mouse or the thumbstick on the console controller. So if we rotate by, say, 60 degrees, well, what we want is for the top half of the character to rotate, but the root of the character to stay. So in one frame, if we rotated, say, 60 degrees, then we'd need to rotate the root bone back. So the root bone will stay still while the actual character, the capsule, is going to rotate. So if we rotate the character by 60 degrees, we need to compensate by rotating the root bone back by negative 60 degrees. Now, as soon as the character rotates a maximum amount, say 90 degrees, that is when we're going to play a turn in place animation where her feet will shuffle like she's turning, And that's also the point where we're going to rotate the root bone back towards the character's direction in a smooth manner and eventually bring that root bone smoothly back to pointing in the character yaw direction. So the first thing we need to do is calculate this offset. As soon as we rotate our character, we need to calculate how much has rotated since the last frame and rotate the root bone back the other way, that amount. And that way, the root bone will stay still as our character is rotating. So let's go ahead and start with that. So here we are in the shooter anim instance.h, and we're here in our private variables section, and we're going to add some variables. Now the first variable I'm going to add is a float, and I'm going to call this character yaw, and this will be the yaw each frame of the character. Now I'll give this a comment, and we're going to say yaw of the character this frame. Now we're also going to have a float variable for the yaw last frame, and I'm going to call this character yaw last frame. So we're storing a variable for the characters yaw this frame and the previous frame. So this comment will say yaw of the character the previous frame. And we also need a float to keep track of the offset that we need to use to rotate the root bone back. And we're going to call this float root yaw offset. This one we're going to make a U property so we can see it in the editor. So let's make this visible anywhere. Blueprint read only. We'll give this the category of turn in place. And of course we need this to be meta equals allow private access equals true. So we've got these three variables and we need to calculate these. So let's go ahead and make a function for turning in place. So I'm going to go up to the public section, and just under public I'll make a protected section. And here I'm going to make a void function, and it's going to be called turn in place. The comment for this is going to say handle turning in place variables. So I'll go ahead and give this a function body. And here in the function body, we can start to script out this functionality. Now, we're going to be accessing the shooter character. So if the shooter character is null, then we don't really want to do anything. So we're going to say if shooter character is equal to null pointer, then we'll simply return out of the function. Now, the next thing we'll do is check our speed. If our speed is greater than 0, then we don't need to be turning in place, because turning in place is simply for when we're standing still. So let's go ahead and make a comment and say, don't want to turn in place, character is moving. So everything is going to be in the else part here. Now in else, we're going to want to get our character yaw. So character yaw is equal to shooter character, and we're going to use get actor rotation. And from get actor rotation, we can simply get the yaw from that, and we'll store this in character yaw. Now, before we actually assign this value to character yaw, this variable holds the yaw from last frame. And we can use that to assign the value to character yaw last frame. So character yaw last frame equals character yaw. So this way, we're taking that yaw value left over from last frame, storing it in character yaw last frame, and then we're updating character yaw with the current yaw value. Now we can create a local variable storing the delta between this frame and last frame. So we can make a const float, because we don't plan on changing this value, and we can call this yaw delta. And we can initialize this with the current character yaw minus character yaw last frame. So this is the difference between the yaw last frame and this frame. Now, we can take this value and subtract it from root yaw offset, like this. Root yaw offset minus equals yaw delta. Now let's take a look at what these values look like, and we can use an on-screen debug message to do this. To add an on-screen debug message, we simply check to see if the G-engine is not null, and then we use G-engine to call a function called add on-screen debug message. Now the first input parameter is a key, and if we use a different number for each message for the key, then we can print multiple messages on the screen at the same time. Let's give this first message a key of 1, and then it's asking for a time to display. And if we use -1 for the time to display, then it will simply print this message for a single frame. And since this function is going to be called every frame, then we'll do this every frame. Now, next it needs an F color for the color for the message. So I'm going to say F color, and we'll use blue for this. Now, the next parameter is an F string. So I'm going to use F string, and I'll use the F string's static function called printf. And printf lets us format a string like we've seen before. So in printf, I'll use the text macro, and we'll do a formatted string here. So for my formatted string, I'm going to say character yaw with a colon, and then I'll use the format specifier for floats, which is %f. And the second parameter inside of printf, if I'm using a format specifier for a float, this needs to be a float, and I'm going to use the float character yaw. Okay, so that is my first call to add on-screen debug message. And I'm going to go ahead and put each parameter on its own line here. That way we can sort of see what's going on. So that is adding the on-screen debug message to print the character yaw. And I'd also like to print the root yaw offset so we can see what values this holds each frame. So I'll go ahead and add another call to add on-screen debug message. For this one, I'm going to put the message using a different key. The key for this one will be 2, so that way we'll get both messages printed to the screen at the same time. And for this one, I'll make the message the color red, and for our formatted string, I'm going to say root yaw offset, and then I'll use root yaw offset for the float value. Okay, so we're just about ready to compile, but before we do, we're going to take these float variables we created and give them default values of 0 so they're initialized. Let's do that in a constructor that we'll make for this class. So let's go up to the top in the public section, and we'll create a useShooterAnim instance constructor. We'll go ahead and create that, and here in ShooterAnim instance.cpp, we'll create the body of the constructor. So let's go ahead and do that. And we'll do a body here, and we're going to go ahead and initialize these variables. So first, let's go ahead and start at the top. So we're going to make a speed variable right here, and we'll initialize that to 0.f. We'll go ahead and take b is in air and initialize that to false. We'll take our next b is accelerating and initialize that to false. Next, we'll have our float called movement offset yaw. We'll take this and set it to 0.f. Next, we have our float last movement offset yaw. We'll go ahead and set that to 0.f. And we have our B aiming, that will be false by default. Next, we have our character yaw. This is going to be 0.f by default. And character yaw last frame, that will also start off with 0.f. And finally, we have our root yaw offset, another float, which will start off at 0.f. Now, the last thing we're going to do is here in Update Animation Properties, we're going to go ahead and call our new function, which we called Turn in Place. So we'll go ahead and take Turn in Place and put it here in Update Animation Properties, and we're going to stick it all the way down at the bottom here, just outside of our check to see if shooter character is valid. Because remember, we're already checking if shooter character is null in the function, and we're returning out of it if shooter character is null. So we're going to call that in Update Animation Properties. Now we can go ahead and compile this. So I'm back here in the default map, and I'm going to go ahead and press play. And here we see that we're printing a couple of debug messages to the screen. One's red and one's blue. And we're able to see both because they're in different keys. We're using different key values for those logs. Okay, so you'll see that if I start running, we don't get anything because we have that check to see if speed is 0. Now, if speed is 0, then we start actually printing those to the screen. Now, if I'm facing forward in the positive X direction, you'll see that the character yaw is relatively 0. Now, as I move clockwise, character yaw is updating each frame. Now, if I rotate about 90 degrees, you'll see character yaw is 90, and check out root yaw offset, it's negative 90. And that's because root yaw offset is the negative value of character yaw. Now, as I keep rotating, my character yaw is going to keep getting closer and closer to 180. Now, as soon as I pass 180, character yaw becomes negative 180. And if I come back the other way, it becomes positive 180. So you can see that character yaw starts off at 0 in the positive X direction and goes upward until we reach 180 degrees around, and then it becomes negative. So if I come back towards the positive direction and I start going counterclockwise, you'll see that character yaw is increasing in the negative direction. It's getting more and more negative. And so we're going to use root yaw offset to rotate our root bone back toward the forward direction. So as character yaw is changing, root yaw offset is going to be compensated in the opposite direction by that amount. Now, in order to rotate the root bone, we're going to open up our shooter AnimBP, and down here at the bottom, next to our output pose node, we're going to use a rotate root bone node. So right click and type rotate root bone and get a rotate root bone node. So we're going to go ahead and plug in the result from use cached pose, cached hip to aim with reload, and we're going to cache the result of this. So we're going to say cache and new save cached pose, and we're going to call this one cached rotated root bone. Now we have this cached pose after rotating the root bone. We can right click and say use cached pose rotated root bone, and we can plug that into the output pose. Now for rotate root bone, we want to rotate the root bone, and you'll see that we have options here for pitch and for yaw. We don't need to rotate the pitch, we only care about the yaw. So next to the pitch, look at this drop down. It says exposed as pin. We can click this and uncheck exposed as pin, and now you'll see that it doesn't show up on the node here. Now we don't need mesh to component, so we can click on this drop down and uncheck exposed as pin, and now you'll only see that the yaw is exposed. Now for the yaw, we can plug in our root yaw offset. So we can right click and type root yaw offset, and since we added a U property to root yaw offset and made it visible anywhere blueprint read only, we can get it here. We're going to plug that right into rotate root bone. Now select rotate root bone, and here in the details panel, look at yaw scale bias clamp, click that drop down, and we'll see here that we can interpret the result. Check that box and scroll down a bit, and you'll see interp speed increasing and interp speed decreasing. These allow us to have a smooth transition when setting our root bone offset. So we can use 10, or we can increase this value like to 20 for increasing and decreasing. I'm going to use 20 for each, but we can experiment and see what looks good. So go ahead and compile this, and we can go ahead and play, and we'll see that as soon as we engage, as we rotate, our camera is rotating, but our root bone is staying relatively in the same place. Now, you'll see that it does shift a little because we're interping. Now, we can set these interp values to lower values, say 10 and 10, and if we press play, you'll see that it's a little bit more flexible. She's sliding a bit more. So we're going to want to keep those at relatively higher values, such as 20 and 20. So this is how we use our root yaw offset to rotate the root bone back once we've rotated our camera for each frame. So we're rotating the controller, the spring arm is following that, and the camera is attached to the spring arm. Therefore, the camera is rotating along with our mouse, and we're keeping the character standing still. Now you'll notice if you rotate all the way around, when that root yaw offset flips from a positive to a negative value, we're rotating our root bone suddenly by 180 degrees in the other direction. Now that looks kind of silly, but when we're done implementing this, we'll never actually get to that point, because as soon as we've rotated by 90 degrees, we'll actually play a turn-in-place animation and rotate the root bone back towards our direction, and so we'll never actually get to negative 180 or positive 180 for our root yaw offset. So this concludes this video. In the next video, we're going to work on getting our turn-in-place animations played as soon as we've rotated our camera by 90 degrees. So we'll see you in the next video.